How about another example? If a gas occupies 473 cubic centimeters, that's a volume, at 36 degrees Celsius, that is a temperature, but we need to convert it to Kelvin, which is 309 Kelvin. Then find its volume at 94 degrees Celsius. That's our second temperature, and that equals 367 Kelvin. We're trying to find the volume. It's V2 that we don't know. So just to be totally clear on that, let's list our givens. We know our volume 1 and our temperature 1, but we don't know our volume 2. We do know our second temperature, however. Write down the combined gas law, and then fill in what you know. And if the same piece of information is missing from both sides of the equation, then that's fine. Here, we're not given any information about pressure, so we're going to just ignore the pressure on both sides of the equation. We assume that pressure stays constant, and therefore this is an example of Charles' law. Plugging in our known values, V1 is 473, T1 is 309, V2 is unknown, so I leave it as the letter V, and 367 Kelvin here. So whether you want to solve this by cross multiplying and then dividing away the 309, or probably just simpler to just multiply both sides of the equation by 367 Kelvin, 367 Kelvin. The 367 and, the Kelvin cancels out with the Kelvin. So just do 367 times 473 divided by 309 gives you 562 cubic centimeters. Example 4. A gas pressure is 765 torr at 23 degrees Celsius. At what temperature will the pressure be 560 torr? Remember, torr is the same as millimeters of mercury, but it's okay to leave the units in torr for this example because it doesn't matter what our units are so long as we're consistent on both sides of the equation. My first pressure, P1, is 765. My temperature 1 is 296 Kelvin. Remember to add 273 there. My pressure in the second condition is 560 torr, and I need to calculate the temperature, second temperature. So I write down my combined gas law. And in this example, I wasn't given any information about the volume, so I can cancel out the volume and ignore it for this problem. I am left with Gay-Lussac's law. I can plug in my pressure values and my temperature values. So 765 goes on top for P1, 296 goes on the bottom. Pressure 2 is 560, and temperature 2 is what I'm trying to solve for. Now, in order to actually solve for T2, I need to get it in the numerator and all by itself. So this is a little bit more complicated. I want to multiply both sides of the equation times T2 so that I get rid of it on the right side and introduce it to the left side. But now I want to divide away this value of 265 divided by 296, because that is, I want to get T2 all by itself. So if I do 765 divided by 296, that actually equals 2.584459, way too many sig figs. So I have this value times my T2, and that equals 560 torr. And this is torr divided by Kelvin. Now, if I divide both sides of the equation by this 2.584459, 2.584459, and that's torr per Kelvin, then I get rid of everything that's attached to my temperature 2, and I calculate my final answer. This 560 divided by, let me just clear this away here. I've got T all by itself, and when I do the math, I get 217 Kelvin. 217 Kelvin. Now, it is considered good practice to report your answer in the same units that you were given in the problem. And since temperature was given to us in the problem in degrees Celsius, then it's considered good practice to take that 217 Kelvin and convert it back to Celsius. So that's what I've done here by subtracting 273, and I have this temperature that's below zero, below freezing in degrees Celsius. Let's do another example. A helium-filled balloon has a volume of 50 liters at 25 degrees Celsius and 1.08 atmospheres of pressure. So I've got a volume, a temperature, which is the same as 298 Kelvin, and 1.08 atmospheres of pressure. So here I'm given three factors, a volume, a temperature, and a pressure. What volume will the balloon have at, so that's my unknown. V2, I don't know, but I do know that P2 is 0.855 atmospheres, and I know that my T2 is 283 Kelvin. And I'm going to use my combined gas law here. P2 V2 over T2, and I'm using all of the variables this time. Nothing cancels out, nothing disappears. So I have 1.08 atmospheres times 50.0 liters divided by 298 Kelvin, and that equals 0.855 atmospheres times my unknown V2 that I want to calculate divided by 283 Kelvin. Doing the algebra, solving for V, it might help you to plug all of this into your calculator and get a value for that first, 0.181208. It might help you to do this division problem, 0.855 divided by 283. And that gives you 0.003012. We still have our unknown variable here, but we also have these weird units, atmospheres times liters divided by Kelvin, and this one is atmospheres divided by Kelvin. So now it's a little easier to see that, hey, I need to divide by this number to get volume all by itself. So now we divide both sides by 0.003012 atmosphere per Kelvin, and divide that over here as well. Do the same thing to both sides of the equation. The atmospheres and the Kelvin cancel out, and we're just going to be left with liters. This cancels out entirely, so that the only thing we have on the right side of the equation is V2. So doing the math gives you an answer, according to the calculator, of 59.9788 or something like that. That's too many sig figs. Go back to your original equation and see 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. All of my values have 3 sig figs, so my answer needs to be reported to 3 sig figs. Because the digit after my cutoff point is a 5 or higher, I need to round up, and that actually has a knock-on effect here and a knock-on effect here. So my final answer is 60.0, 1, 2, 3 sig figs. And my units for volume in this example are liters. Another example. Gas has a pressure of 1.26 atmospheres and a volume of 7.40 liters. If the gas is compressed so that it has a smaller volume, 2.93 liters, what will its pressure be? In this example, we are not using all components of the combined gas law. We've got P1, V1, T1, P2, V2, T2, but temperature was never mentioned in this example, so we just ignore the temperature. We plug in our values, 1.26 atm times volume, which is 7.40 liters, equals, don't know my pressure, but I do know my volume is 2.93 liters. Divide both sides of the equation by 2.93 liters, 2.93 liters, so that I get pressure all by itself on the right-hand side of the equation. And do the math, and the calculator says your answer is 3.18225, but I can see that I should round my answer to 3 sig figs, so my final answer is 3.18, and my units are atmospheres, because the liters cancels out with the liters, and the only units I have left are atm. Another example. A sample of neon gas occupies a volume of 252 milliliters, volume 1, at 25 degrees Celsius. This is temperature 1, but we need to convert to Kelvin always, and add 273, you get 298 Kelvin. What will the volume be at 50 degrees Celsius, so that's temperature 2, if the pressure is constant? So here it tells us that the pressure is constant, so you could kind of skip ahead if you wanted to and not include the pressure at all. But I like to cross things out. It makes me happy, so that's what I'm going to do. We're not using pressure at all, so I'm going to cross that out. V1 divided by T1, that would be 752 milliliters divided by 298 Kelvin, equals, I don't know what V2 is, but I do know that temperature 2 is 50, I'm sorry, not 50 degrees Celsius. I didn't convert that to Kelvin, is 323 Kelvin. And I accidentally deleted this. So I'm going to have 323 Kelvin here. And now I solve for V2. Right now, V2, I'm dividing away the 323. So the opposite of that is to multiply by 323. So I do the same thing to both sides of the equation to keep the equation equal. Those values cancel out. And I'm left with a big multiplication problem here. But the Kelvin and the Kelvin cancel out, and the only units I'm left with are milliliters. According to my calculator, I get an answer of 815.0872, but I'm only going to report my answer to 3 sig figs, so just 815 milliliters. One more example, and this one is super relevant to your everyday life. There's always a warning on an aerosol can to not store it above a certain temperature. And so let's find out why that is. The gas pressure in an aerosol can is 3 atmospheres at 25 degrees Celsius. So we have a pressure and a temperature, which is equal to 298 Kelvin. What is the gas pressure at 52 degrees Celsius? 52 degrees Celsius would be the same as 325 Kelvin. So that's temperature 2. And again, if we start with the combined gas law, P1V1 over T1 equals P2V2 over T2. We see that we've got pressures and temperatures, but no volumes. So we'll cross out the volume because we won't use it. And we can plug in the values that we have. 3.00 atm over 298 Kelvin equals an unknown pressure over 325 Kelvin. So if we want to get pressure all by itself, we need to undo this division by 325. So we multiply by 325 Kelvin, and we do the same thing to both sides of the equation. The 325 Kelvin cancels out, and we are left with 3 times 325 divided by 298, which my calculator says is 3.2718. Using the rules of sig figs, look at how many sig figs are in each component of my multiplication division problem. I consistently have 3 sig figs, so I will round off to 1, 2, 3 sig figs, and 3.27 atmospheres. Notice that your Kelvin units cancel out, and so you're left with atmospheres of pressure.